Good afternoon. So today we're going to do chapter 6, and the title for chapter 6 is electrophilic addition. So how do they work? Electrophilic addition. So we have two terms here. We have electrophilic, which means something positive, and addition means we have to add two atoms, two things, one on each. And this is on alkenes. So let's look at the structure of an alkene to start with. So an alkene usually has this structure, and the carbon here, this is page 1 by the way, the carbon here is an sp2, and so is this one. So the angles are around this carbon, all of these are 120 degrees. And the pi bond is perpendicular to the plane. So this is a perspective representation of the alkene. So if I put a CC, I'm going to have something coming in front of the paper up here and something behind, then same here and this. So what I'm representing is this particular bond here is this one, this particular bond is this one, and I'm flipping it about 90 degrees. So what do we have on the top? We have a pi bond. And you know that a pi bond is made of two p orbitals overlapping a partial overlap. So this is a pi bond, and it's side-by-side overlap, and it's partial. So if it's partial overlap, it means that this bond, the pi bond right here, is weak because it has a partial overlap. So not only it's weak and it's partial overlap, but what we have here, what is shared between these, are two electrons. So that makes it nucleophilic. So a pi bond, an alkene, is a nucleophile. It's not very strong nucleophile, but it has electrons here. So what's unique about this is because this pi bond is above and below the plane of the molecule, it's easily accessible. So what happens if we bring an electrophile, an electrophilic compound? So if I have, again, it's my alkene, and I have the pi bond here, same thing on this side. So we have electrons here, that's the pi bond. So if I bring a Lewis acid, a Bronsted acid like HBr, remember, a nucleophile is a base. If we bring an acid, what's going to happen here is that the pi bond, the H will be close to the pi bond, so the pi bond opens and attaches to the H, and then the H attaches to the pi bond, and the bromine takes the bond there. So we end up with this. We're going to end up with C. So that p orbital here will pop open. So this thing will open, and then the H will stick here, and then these will move up because we're changing now the hybridization. And on this side, this p orbital is now empty. So the electrons went here So the green electrons here, whatever was shared, ended up here. And now we have here an empty orbital. So it's a p orbital that's empty. So the carbon has 2, 4, 6. So it doesn't have an octet. So that's missing electron. It's called a carbocation. So what happens next? We have still Br minus sitting out there. So now the Br minus will attach to this, and then we end up with CH, the wedge here, and then the Br will come here, and this comes up, and this is like this. So basically, that's what we call an electrophilic addition. So this is step 1. That's the first step. Step 1, you go from the alkene to the carbocation. And step 2, we go from the carbocation to the alkyl halide. So this is an alkyl halide. And this is a carbocation. And as you can see, it's an addition. So what was added here, you have 2 atoms that are added. You have the hydrogen and the bromine. But how did they add? The hydrogen added on the pi bond, the green stuff, and the bromine just took its own lone pair and attached it to the other carbon. So the electrons here come from the bromine. The electrons here come from the pi bond. And every electrophilic addition takes this process. You have first the pi bond takes the electrophile. So here the hydrogen is the electrophile. And the second step is the nucleophile from the acid attaches to the empty p orbital, which is a Lewis acid, and then you end up with an alkyl halide. So this is the overall process of an electrophilic addition. Okay? Now let's look at another scenario. What if instead of having no particular bonds here, no particular substituent, what if I have here an H, and then an H, and then another H here, but here I have a CH3. Okay? So you see we have 2 carbons. This, the green one, I'm going to call it carbon 1, and this is carbon 2. And of course, the pi bond is right in the middle. So if I bring HBr, okay, the pi bond opens and takes the H, and then the Br takes the bond between H and Br. So the question is, where would the H add? Will it add to the C1 or to the C2? So let's look at the 2 scenarios. So if it adds to C1, so this H, the pi bond opens to the left and attached to the green carbon. So we end up with the green carbon C, and then H. As you can see, if this comes down, this moves up. So we have CH3, and then H. And then on the other side, we have C, H, H plus. Okay? Now, if the hydrogen adds to C2, then on this side, I'm going to have, so this is the green carbon, I'm sorry, the red carbon there. In here, the green carbon doesn't add the hydrogen, so you end up with the same structure. and this is plus. And then on the other side, and then the H. So this particular H here, this one, ended up here for C1 and in here for C2. The question is, which one is the correct step? Is it going to add to the green or to the red carbon, and why? So before we answer that, we need to see, first of all, how are they similar? How are they different? So if I look at this particular carbon right here, this is a positive carbon, so it's a carbocation, and it's bonded to only one carbon. So this particular carbocation, this is what we call a primary carbocation. This one, the bottom one, it's the green. It's attached to one carbon, two carbon. So in here, we have a secondary carbocation. So the question is, which one is better? Is the reaction going to evolve towards the first scenario or the second scenario? And the answer, you're going to see it on page 2. So let's go back to the difference between primary, secondary. So let's go back to that primary carbocation, which looks like this. So I have I'll start with the secondary. So we had something like C plus, page 2, so C plus, we have an H, and then here we have a CH3. So how does CH3 looks like? It's a C with an H here, and an H here, and another H here. Now on this side, we had the C, H, H, and H. So if I want to show you again, this is the structure. This is what we have compared to that one. So what is special about this? We have here a p orbital, an empty p orbital that's perpendicular to the plane, which is on the plane of the paper, but perpendicular to this plane where this hydrogen carbon and this carbon are. So the angle right here, if we look at this angle right here, it's a 90-degree angle. And this carbon here is an sp, it's an sp3 carbon. So this is an sp3, which means that the angle right here, it's 109. So 109 compared to 90, it's not a big of a difference. So here's what happened whenever you have a carbocation with an empty p orbital that is almost parallel. It's not exactly parallel, but this orbital right here, it's very close to being parallel to this hydrogen. So what happened here, this hydrogen keeps on moving back and forth from this carbon to this one. Now, in the process, as you can see, before it moves, this carbon has only 6 electrons, so it doesn't have an octet, so it's an unstable carbon. But as the hydrogen hops with the electrons, it moves back and forth. So sometimes this carbon will be sp2, but then when the hydrogen hops here, it becomes sp3. So what does it do to this carbocation? It alleviates that positive charge. So this doesn't feel exactly completely positive, because in a fraction of a second it's positive, and then when this hydrogen hops here, it's no longer positive. So basically that positive charge will be kind of shared between these two carbons. And because we have here free rotation. If you remember from chapter 3, the conformers. So when there is a free rotation, now this hydrogen can move here. That's called hyperconjugation. If it rotates, this hydrogen also will move here, and then this one. So you have all of this free rotation that allows these three hydrogens to hop back and forth from the p orbital to the sp3. And it's the same thing here. See, this hydrogen right here will be able to hop back and forth between the p orbital and this sp2 orbital. So in this scenario, we have 1, 2, 3, 4, 5, 6 hydrogens that can be hopping back and forth to this carbocation, making it less positive. So this is a secondary carbocation, and it has a possibility of 6 hydrogens moving back and forth from the P to the sp3, which makes the P less positive because the hydrogen comes with the electron. Now that is called hyperconjugation, this hopping back and forth. It's called hyperconjugation, and we already studied hyperconjugation in the previous chapter when we compared stability of alkenes. If you go back and take a look at that. Now, if I go back then to the first scenario right here with this primary carbocation, I'm going to redraw the structure. So it's C, H, and then we have the p orbital, so that's the primary, H. And then here we have C, and then we have H, H, and CH3. So in this particular scenario, this hydrogen can hop right here. This is an sp3, and this is a p orbital. So this can move back and forth here. And because of free rotation, this also can move back and forth. So what does it mean? It means we only have 2 possible hydrogens capable in this particular structure to do the hyperconjugation. If we had here another hydrogen, it would be 3 possibility, the maximum. So in this scenario, we have, this is a primary carbocation, and we have, in this particular scenario, 2 hydrogens that are going to move back and forth from P to sp3, from the p orbital to the sp3, and alleviating that positive charge on the p orbital. But if we compare these two, the secondary has more hydrogens hyperconjugating than the primary. And it's always going to be the case because in this scenario we have 2. The maximum possible is if we had hydrogen here. So in all the cases, the primary carbocation, the maximum it has would be 3 hydrogen. A secondary carbocation would have 6 hydrogen. And if you think now of a tertiary, meaning a carbocation that's surrounded by 3 different methyl groups. So I have C, C, H, H, H. And then here, I would have a C, H, H, sorry, H, and then H. And then here, we have C, H, H, and H. And we have the p orbital. So this particular one is attached to 1, 2, 3. So this is a tertiary carbocation. So a tertiary carbocation is a carbon. Right here, this carbocation is attached to 1, 2, 3 carbons. Of primary, so this is our carbocation, it's only attached to 1 carbon. The secondary is attached to 2 carbons. So if your carbocation is attached to 2 carbons, the maximum possibility of hyperconjugation would be 6 hydrogens, a total of 6 hydrogens hopping back and forth to that empty P. If it's a primary, the maximum, if we had an H here, it would be a maximum of 3. In this scenario, only have 2. And in this case, you see how many hydrogens can hyperconjugate? This can move here, and because of the free rotation, this also can move, etc. So we have 1, 2, 3 on this side. Also, this can move here, so we also have 1, 2, 3 on this side. And finally, this can have hop back and forth, and we have also this many. So in here, the maximum is 9 hydrogen that can hop from the P to the sp3. So the more hydrogen go back and forth to the p orbital, the less positive it becomes, which means more stable. More stable because it doesn't feel that it's missing that extra electron, So as a rule then, the primary carbocation, the maximum it can have is 3 hydrogens performing hyperconjugation. A secondary have 6. A tertiary will have 9 hydrogens right here. This is the scenario. So what does it mean? The more hydrogen hyperconjugate, the more stable. So a tertiary is more stable than a secondary than a tertiary. So this is the most stable carbocation because of hyperconjugation. So if you review your concept of hyperconjugation from chapter 5, this repeats itself. The only difference is in chapter 5, we were talking about hyperconjugation with a p orbital, whereas here it's a hyperconjugation with a carbocation. So I hope you understand this. So what does that mean? How does this relate to the electrophilic addition of alkenes? So that's our next slide. So we're going to go back to that first scenario where I start with C, H, CH3, CHH, and I bring an HBr. So the pi bond opens, takes the H, the Br takes the pair there. And the first step, are we going to go to C1 or C2 again? So this is C1, and this is C2. So if I go to the C2 scenario, the hydrogen lands in the C2. We end up with CH, CH3, H. That's our C2. And the carbocation will be on this side. If it lands on C1, then we're going to have CH, CH3 plus, and then CH, H, H. So this is our C2. This is our C1. So if the hydrogen, we're talking about the hydrogen landing on C1, we end up with this carbocation. If the hydrogen lands on C2, we end up with this carbocation. So you can see that the top carbocation right here, it's bonded to 1 carbon. So this is a primary carbocation. In here, the carbocation is bonded to 1 carbon to the right, 1 carbon to the left. So this is a secondary carbocation. So the question is, which one is more stable? We already established that the secondary carbocation is more stable than a primary carbocation. So what does that mean? It means that this will form and this won't form. So this is not going to form because it's not stable. This is not stable. So we call that a regioselective addition. So all additions are regioselective, meaning that they will select which side. It doesn't happen randomly. We're not going to have 50-50%. We're going to have one product and not the other. So this is our step 1. So step 1, you form the carbocation, And step 2, as we said earlier, we take the carbocation and now the bromine. So here we end up with the CH3. So the bromine now comes on this side and attached to the carbon, and you end up with CH, CH3, Br, CH3. So there is a preference, the H added on this side, the bromine added on this side. And what is the difference is the halogen adds to the carbon that has the most substituent. So you see here we have no substituent, it's just hydrogens, but this one we have one substituent. So the hydrogen adds to the least substituted and the halogen adds to the most substituted. And this is called Markovnikov's rule. Markovnikov rule. So what does the Markovnikov rule says? It says basically that you add the hydrogen on the least substituted carbon and you add the halogen on the most substituted carbon. So let's try to see some more examples. Okay. So here, what are the examples? Here's another example. C, CH3, CH3, HH. So we come with HBr, same scenario. We're still looking at the alkene as a nucleophile and the HBr as a branch-dead acid. So the pi bond takes the H, this opens. So again, we have two. Where is the carbon gonna add if we look at either possibilities? So if I look at the hydrogen here, lands on the green, that's C1. We end up with C, CH3, CH3 plus, and then C, H, H, H. So you see here that this carbon has 1, 2, 3. So this is a tertiary carbocation. Now, if it lands on the red one, you're going to have CH3, C, CH3, H, and then C, H, H plus. So you see now the green, this carbon right here is only bonded to 1. So this is a primary carbocation. So guess what happens here? This is not going to produce because the primary is not stable at all. So this is unstable. So it won't form. But this one is stable, so it will form. So automatically, if this won't form, what is step 2? Step 2 is that carbocation, the tertiary right here, will grab the Br minus and we produce C, CH3, CH3, Br, CH3. So now let's try another example. So this is the example where we have C, H, CH3, C, H, CH2, CH3. So if we add HBr, again, we have two options. Either the green, the H lands on the green, or the H lands on the red. So let's look at the green one. So if it lands on the green, either way, anyway, the mechanism is this pi bond opens, this goes this way. So if the H ends on C1, we're going to have C, H, CH3, H. And on the other side, the red one will be the carbocation. So that's the green path, meaning the hydrogen landed on the green carbon. Now, the red path, the hydrogen lands on the red carbon, so we're going to end up with C, H, CH3, and then C, H, CH2, CH3, and then H. Notice that when this was in sp2, everything is in the same plane, but as the H moves, we have to transform it into an sp3. That's why the wedge and the dash move up so that the H can come, and that's an sp3, which is a tetrahedral. Now, what is the difference between the top carbocation and the bottom one? You see, this one is attached to 1, 2. So this is a secondary carbocation. In here, same thing. Take a look. This carbon is attached to 1 here, 1 here. So this is also a secondary carbocation. So how much product are we going to get? Are we going to get different amounts or same amounts? Let's finish the process. So that's our step 1. So if I look at step 2, the Br minus attaches to the carbocation. So here, we put Br minus attaches to the carbocation. So the green will give me C, H, CH3, H, and then C, H, CH2, CH3, and then Br. The red one, right here, will give me C, H, CH3, Br, and then C, H, CH2, CH3, H. Now, normally, because they're both the same stability, we're going to get 50-50, which is true. So this is 50%, and this is 50%. But there's something else to notice here that's very important. If you look closely at this carbon right here, we're still talking about the red one right here. Look at the substituent it has. It has CH2, CH3, CH2, CH3, H and Br. Okay? But this particular one, take a look. The green one right here. It has CH3, Br, H, and then CH2, CH2, CH3. So what I can do, I can rewrite this, the green carbon, and then put an H here, put a CH3 here, put a Br here, and all of this is really propyl. Excuse me. And in this scenario, the red carbon right here, it has an H, it has CH2, CH3, it has a Br, and it has CH2, CH3. So this whole section here is CH2, CH3. In here, this whole section is the propyl. Now, what is the difference between the top one and the bottom one? The top one has two identical substituents, so this is not chiral. If you look at the bottom one, the green path, it has propyl here, bromine, methyl, and H. So this is a chiral carbon. So if it's chiral, you're going to have how many products? Now remember, how did we get this chiral? We put the bromine here that attacked the carbocation. Now this is trigonoplanar, so it's flat like the paper. The bromine can attack from below, from underneath, or from above. So we're not going to have only one product. We're going to have this, and we're going to have the mirror image. So this is when the bromine attacks from the bottom, but we could have also the bromine come from the top, and then the H, CH3, CH2, CH2, CH3. So if you look closely, both of these are chiral, and if we repeat what we studied in chapter 4, when we have a chiral, we're going to write the substituent, which one comes first. So this is our number 1, this is number 2, this is number 3. So this is an S. In here, this is our number 1, number 2, number 3. So this is an R. So 50% of the product will be this one, but the other 50 will be a mixture of these two. So if you remember, this is called racemic mixture, which means it's 50-50%. So 50% of the S and 50% of the R. So altogether, half of the product will be this one. So this would be the 50%, but each of these is half of that other 50, so this would be 25% and 25%. So these are the complexity of the addition. Is like the process itself is simple. You go through 2 steps. First step is form a carbocation. Second step, you add the halogen. So the mechanism is pretty simple, but the product can be different depending on the scenario. So you have to pay attention to, number 1, the stability of the carbocations, and number 2, at the chirality of the product. So you see here, both of these are secondary, so we're going to have equal amount because the secondary have the same stability. But in the previous scenario, I show you here again, in here we have a tertiary carbocation, here primary. This won't form at all, and you're going to end up with 100% of the product of the tertiary. So that's what happened with these electrophilic addition, is that you have to consider the product. How many product am I going to get? And the product depends on, again, on the stability of the carbocation. If you have a primary carbocation, you don't get the product. But if you have a secondary and tertiary, you're going to get product. But if you have a mixture of secondary, tertiary, the tertiary would be always the major, the secondary would be the minor. So we can summarize it here, is that in any kind of electrophilic addition, the product from a tertiary is the major, the product from the secondary is the minor, and the primary doesn't form. So I hope you remember this. If you produce a primary carbocation, you're not going to get a product. But if you have a tertiary or secondary, the tertiary would be always your major product, the secondary would be your minor. And if you have both tertiary, then they're going to be 50-50. If you have both secondary, it would be 50-50. But in addition to all of that, you're going to add also the component of chirality. So if you have a chiral compound that is produced, it's always going to be 2 products because the second attack can be from the top of the carbocation structure or from the bottom of the carbocation structure. Now we have another thing to consider, and then we'll have the whole picture of nuclear electrophilic addition. Let's look at this scenario. So now I'm on page 5. So here's the next scenario. We have here CH3, CH, CH3, CH, CH2. Okay, same scenario. We have HBr, and we already know the H is going to add for sure on the least substituted. We already established that. So because if it adds on this side, you're going to end up with primary, which doesn't work. So we're going to end up with this. We have a CH3, CH, CH3, and then we have CH plus CH3. This is a secondary. You have one carbon to the right, one carbon to the left. That's a secondary. Now, what happened with this, this is, if I bring the Br minus, of course, secondary can form a product. So the Br minus is going to attach to the carbocation. And as you can see, we end up with 1, 2, 3, 4 substituents. So we're going to end up with CBr, CH3, H, and here it's an isopropyl, CH, CH3, CH3. So that's the product. But remember, the Br can add at the bottom or the top. And if you see, this is also chiral. So we're going to end up with this S and the R. We're going to end up with 2 products. So this is what we learned previously. And you can draw it the correct way with the wedges and the dash, and then you can see that you produce 2 products. But then in this particular scenario, so we're going to take this carbocation right here and draw it again. So that carbocation has an H here, has a CH3, and it is positive, which means we have a p orbital. And what's next to it? You have a C with an H, and then a CH3 and a CH3. So this and this are exactly the same. That's our secondary carbocation. But notice here what we did earlier. This hydrogen is almost, this orbital is close to this. What do we call this? As it hops, that was called hyperconjugation. But in this case, the whole bond right here will shift. The 2 electrons will move here. So if these 2 move here, we'll end up with this. C, CH3, CH3, and then now that orbital that has the H is empty, and that H transferred here, so I'm going to put the bond in red, and then we have H and CH3. So this process, again, because of the vicinity, the H moved from one carbon to the other. It's called the 1,2 hydride shift. 1,2 hydride. Hydride, why we call it hydride? Because the hydrogen takes the whole pair of electrons. So these electrons were with the hydride and they moved, so that's a shift. So this is called rearrangement. So what does it mean, rearrangement, and when does it work? Look here. This was a secondary carbocation. We saw it here. That's the same. It's the secondary carbocation. But when the hydride moved to that empty p orbital right there, now this is empty. But what's the difference is we went from a secondary carbocation. Why is it secondary? Because this particular carbon is bonded to 1, 2 carbon. In here, this carbon is bonded to 1, 2, 3. So this is a tertiary carbocation. Now, which one is better? The tertiary is more stable than the secondary, so this reaction will happen. So what does it tell us? It tells us that if you form a secondary carbocation, if you have a secondary carbocation and you have a hydrogen next to it, pay attention that you can use the hydride shift, and it will happen because you're going to produce a tertiary carbocation. So why does this happen again? It's because a tertiary is more stable because of all these hyperconjugation. You see these 3 hydrogens hyperconjugate, this 3 hyperconjugate, this 3 hyperconjugate. These 2 hyperconjugate. So you have many possibilities of hyperconjugation, whereas here you only have 3 here and 1 there. So that's the difference. This is more stable than this. So what does it mean? It means first you're going to produce the secondary carbocation. That carbocation will produce the 2 products, the S and the R, but also that secondary carbocation can transform into a tertiary through hydride shift. And now this tertiary carbocation will grab the bromine. So we have a Br minus. And the Br minus will attach to the carbocation. And we end up with C, CH3, CH3, Br, CH, H, CH3. So you notice that this is different from this. Here we have an isopropyl. Here we have 2-methyl with the bromine. So these are completely different products. And the question is, which one will be the major product? This, because it's generated from the secondary, this will be your minor product. This, because it's generated from a tertiary, it will be your major product. So I hope this is clear about electrophilic addition. The mechanism is pretty simple, but as you work your way, make sure you pay attention. What type of carbocation do I produce? So if you produce a primary, it's not going to work. But if you produce a secondary and you have a possibility like here, the secondary has a hydrogen right next to it in the next carbon. That's why we say 1, 2. It means if this is my 1, this is 2. So the carbon moved from the hydride moved from carbon 1 to carbon 2 to produce something more stable, which is a tertiary carbocation. So this is a rearrangement. And if you remember when we introduced chapter 5, I mentioned to you that not only we have additions, but we also have rearrangement reactions. So in this particular chapter, we're exposed to both the addition and the rearrangement. Now let's look at another scenario. This one. So here we have C, CH3, 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 CH, and then CHH. Again, HBr. So what happens here? HBr, the hydrogen, where is it going to end? If we put it here, you end up with primary, but if we put it here, we end up with secondary. So we know that it will land on this carbon. Basically, that's not correct. That's not how you present it. It's the pi bond that takes the hydrogen, sorry, and this moves here, okay? So the pi bond opens, but we know that this hydrogen is going to land on this carbon. So we end up with C, CH3, 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 and then CH, plus, and then CH3. So you see the H ended here, and this is now the carbocation. So this carbocation is attached to 2 carbon. So this is a secondary carbocation. So again, the bromide will attack right here. It attaches to the secondary, and we already said that secondary carbocation can form. They're not the most stable, but they will form, and they will give us a product. So that's our product from the secondary carbocation. But then let's draw it again right here. So here we go. I have C, CH3, 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 C, H. So I'm drawing this one, and then CH3. So the real representation is this. So that's your secondary carbocation. This H is this one, this methyl is right here, and the tert-butyl is here. Now notice, in the previous scenario, there was an H here, and it moved to the empty orbital. But we can also do this. The whole methyl can also hop right here. So in the previous scenario, I show you, it's the H that hopped into the carbocation, the empty p orbital, and we called it 1,2 hydride shift. Here, the whole methyl moves here, so this is called the 1,2 methyl shift. So why is this going to happen? Let's see what happened when the methyl moves here. When the methyl moves here, now this is going to be the carbocation. Okay, so you're going to have CH3, CH3. See these two right here are these two. And then the methyl now hopped on this carbon, which is the one I'm representing. So you have methyl, and then H, and then CH3. So this was a secondary carbocation. And here, see it has 1, 2, 3. So this is a tertiary. So if whenever you go from secondary to tertiary, you make it more stable. So this reaction will happen. And this is also called the rearrangement. So what type of rearrangement do we have so far? If your secondary carbocation has a hydrogen on the carbon next to it, we call it alpha carbon, then the hydrogen can shift. So it's called 1,2 hydride shift. Why hydride? Ide means it takes the electron, it's negative, so the electrons move with it. In here, it's called methyl shift. So the whole methyl group, CH3, with the pair of electrons moves on the empty p orbital, and you end up with tertiary. And of course, the second step would be the bromide come in, and then it will attach to the carbocation, and you produce CH3, CH3, Br, C, CH3, H, CH3. So what are the two products here? This is one of the products. It comes from a secondary carbocation. This is the second product. It comes from a tertiary carbocation. So this is going to be the major product, and this is going to be the minor product. Why minor again? Because the secondary carbocation is less stable than a tertiary. So the most stable will give you more product. The less stable will give you less product. So let's review quickly what we learned so far about electrophilic addition. So if you remember, electrophilic addition happens in 2 steps. I'm going to just summarize it here. So you start with the alkene. the first step, so we're going to use HX, meaning any halogen, I'll come back, by the way, for these acids, any Bronsted acid. So the first step is the pi bond takes the H, the halogen takes the pair. So you're always going to end up with a carbocation. So the hydrogen lands on one carbon and the other one is empty. So that's always step one. And then the second step is the halogen. In here, I'm sorry, I should put X in general. That's the halogen, adds to the carbocation, and you end up with the alkyl halide. So what did we learn about this carbocation? First of all, what type of X? These reactions, you have to have a strong acid. So it has to be a strong Bronsted acid. So if we compare them, if I have HF versus HCl versus HBr versus HI, I taught you this in chapter 2. This is the largest, which means this acid is the strongest. Because the bond is long, it's easy to snap. This is the smallest. So this bond is the shortest, which makes this acid the weakest. But we said here that it has to be strong Bronsted acid. So HF won't work because this is a weak acid. So these reactions only happen with HCl, HBr, and HI because these are considered strong Bronsted acid. This one is weak, so it won't work with HF. So all of these mechanisms work exactly the same with the halogen, whether it's Cl, Br, or I, but of course it works faster if the acid is stronger. So HI will be the fastest one, followed by HBr, followed by HCl. So kinetically speaking, that's what happens. Now, if we want to represent it in terms of energy profile, this is your alkene, so that's 1. This is 2. This is 3. So 1 is our alkene. Then we produce an activation energy because a carbocation is not stable because it doesn't have an octet, it has only 6 electrons. So that's your intermediate right here. That's your carbocation number 2. And then, and this is not favorite reaction because you go from stable to unstable. That's why it's an endergonic reaction. Remember the delta G here? So this has a positive, delta G is positive, which is not favored. But why does it happen? It's because then you produce an alkyl halide, which is stable. So the first step is the longest one. So that has high activation energy. And the second step has a lower activation energy, so it's fast. So this is the slow step, and this is the fast step. And I hope you understand that 2 is the carbocation. That's your intermediate. It's not stable, but it can be detected. And 3 is your alkyl halide right here. So this is the general profile for the reaction for all of them, whether you use HCl, HBr, HI, you're going to always have this. Now, what is the difference is what type of product we get. So we said if you have a primary carbocation, if you're intermediate, if you're 2, the intermediate, if your intermediate is a primary carbocation, then you won't have any product. If it's secondary, it's going to give you the minor product. If it's tertiary, it will give you the major product. Another consideration is secondary, so this is the most important part, is that secondary carbocation can turn into what? Tertiary carbocation. How? There are two processes. It's either 1,2 hydride shift or 1,2 methyl shift. So every time you produce a secondary carbocation, pay attention and see if you have a possibility of a 1,2 hydride shift or 1,2 methyl shift, because if that is possible, then it will happen to produce a tertiary, which becomes your major product. Now, again, the last thing is to say here that I skipped, where does the hydrogen add? Hydrogen always adds to the least substituted carbon, and that's called the Markovnikov rule. So remember Markovnikov rule, which means that you go to the carbon that has less, that is attached to less carbons, because if you add it to the other one, it will be a primary, and primary don't form. So this is pretty much the summary of the entire portion of the chapter that we studied, that what is an electrophilic addition? You add an electrophile to the pi bond. The first step is always going to be a carbocation. The second step is when the second part of the added component adds, like here in the halogen. What does it take to make these additions? You always need a strong Bronsted acid for this particular reaction, and which means that you can't use HF. This is the energy profile. So this would be the time, and this would be your delta G. Remember, we did this in class for chapter 5. So this is delta G. The first step, which is the formation of the carbocation, is the slowest because it requires a lot of energy and it produces something unstable. And the second step goes pretty fast because you produce something very stable. And what is the product of the first step? It's the intermediate, which could be primary, secondary, tertiary. If it's primary, it doesn't produce any product. You don't produce the product from a primary. But if you have a secondary, it will be the minor. If you have tertiary, it will be the major, if you have both. If you have just secondary, that would be your only product. And finally, the secondary carbocation have the possibility to rearrange into a tertiary. They always have the possibility to rearrange, so this is called a rearrangement. And that rearrangement is made to make the carbocation more stable, so it gives you different product, and that product is always going to be your major product. So I hope that this helps you understand the first part of what is an electrophilic addition on alkenes. And then our next lecture will be other type of additions. It's still electrophilic addition, but instead of using a Bronsted acid, we're going to use different types of acids. Thank you.